All right. So welcome to lesson 6, which is on chapter 8 of the textbook, and which will cover our derivation rules. We're going to add some new rules for the and symbol, for the or symbol, and for the if and only if symbol. Um, yeah, so let's get to it. You remember, of course, that we have rules already for the if-then symbol and the negation symbol. We have modus tollens, modus ponens, double negation introduction, and double negation elimination. So those are all the rules we can use for these symbols when we're doing our direct derivations, right? Lets us do lots of stuff. We've done a lot of exercises with them already. Um, but there are just a few more to add to our propositional logic. There's going to be two rules for each of these symbols, but I promise they aren't very hard to wrap your head around. So, you know, it sounds like a lot to do two for each of these, but it's not, and they'll make pretty good sense, I think. Okay, so let's start with our new rules for the and symbol. Our new direct rules, derivation rules for the and symbol. Okay, so suppose we know two things, and we know them separately. Suppose on the one hand we know that Plato prances, and also suppose on the other hand we know that Remy cooks ratatouille. So we know each of these things independently. Well, if we know both of these things are true, then we know that the sentence Plato prances and Remy cooks ratatouille is also true, right? If we know two things independently, we can just say, this thing one that we know is true and this thing two that we know is true. And we know that whole sentence, that whole claim is true. By considering each known thing, then, we know that their adjunction is true. The case where we say, this is true and that is true. If we know two things, we know that their adjunction is also true. As we can see clearly with the case of Plato prancing and Remy cooking ratatouille. So we can just deploy this in our demonstrations, and we'll call that instances where we do that the adjunction rule, which we will abbreviate as ADJ. You can see down here, adjunction. The adjunction is this, it's when we stick a and in between them. So it's the adjunction rule, ADJ. So it lets us do we can derive new lines in a derivation using the following argument forms as like the way of setting up that derivation. So like if we have something P and we have something Q, well, then on a new line, we can just have P and Q, right? Because we know P is true, at some point in a proof. And if we know Q is true at some point in a proof, well, then we know that P and Q is true. You can also change the order. So if you have P and Q separately, you can make Q and P, right? So like if you consider back here, I know Plato prances is true, and I know Remy cooks ratatouille is true. Then I know Plato prances and Remy cooks ratatouille is true. But I also know Remy cooks ratatouille and Plato prances is true, right? So it doesn't matter which side you put them on. So depending on the proof, one of these orders will be more useful than the other. And here's how it will look in our proofs. So you can see if we have P and Q as premises, we can get P and Q by using the adjunction rule down here. You can see we have P, we have Q. So we have P and Q by adjunction on lines 2 and 3, right? So that's how it will appear for us. Okay. But there's also another rule for the and symbol that also makes lots of intuitive sense. So let's say we sort of flip direction and we start with knowledge that Plato prances and Remy cooks ratatouille is true. That whole sentence is true. Well, if that's the case, then we know both that Plato prances and separately that Remy cooks ratatouille, right? Because for this whole sentence to be true, each part of it needs to be true, right? This part needs to be true, and this part needs to be true. So from this big long claim, Plato prances and Remy cooks ratatouille, we can derive both the following things. We can derive that Plato prances, and we can derive that Remy cooks ratatouille. So you can simplify the and claim into both of its parts if you know that you have an and claim. We'll do that in our derivations as well. So if we have P and Q, for example, we can get both P and we can also get Q separately. So it's true that with P and Q, we can get P, and also with P and Q, we can get Q. Again, the order doesn't matter, but you have to pull them out separately. So yeah, we'll call this derivation rule simplification because we're simplifying an and claim into its parts, right? So we call it simplification, and we will abbreviate it with S in our derivations. So this is how S, or simplification, looks like in our system. So if we have P and Q as a premise, we can get P by applying the simplification rule like we do over here on the left side. You want to show P, you have P and Q as a premise. So you just apply the simplification rule to line 2 where P and Q appears, and you get P. Similarly, if you wanted to do it the other way, you can look at this example. You want to show Q, you have P and Q, you can get Q by simplification on line 2, right? Okay, so how will that look in our derivation system? Well, I will show you examples of these like as I type them out, but it's basically just going to be what I already showed you. So I've already pulled up the Carnap practice set here. It's just from Brightspace. You can go into lesson 6 and find it there, chapter 8, derivation practice. So I've scrolled down to the questions, the very basic sample questions I gave where I apply these rules. So you can see here, I should say also, on the right side of the screen, you'll see all the rules that we're going to learn today. We have the 4 of them that we already know: modus ponens, modus tollens, double negation elimination, double negation introduction. And then if you look under that, you'll see we have simplification and adjunction, and you can see it goes whatever order is needed. But yeah, so we'll apply those here. So let's look at 1.4 here. We want to show, as usual, P and Q. We have P as a premise. We have Q as a premise. So you'll remember we just learned our AND rules, right? So if we want to introduce an AND symbol here, we want to get this AND symbol, we can use our friend adjunction, where if we know the left side of this AND symbol and the right side of this AND symbol, we can get, if we know them independently, which we do in these premises, we can spit out this AND claim. So we'll have P and Q. And we have that from adjunction on lines 2 and 3. Whoops, didn't have my number lock on there. On lines 2 and 3. And you can see the system is happy with that. We used a rule that it likes. And there you go. Now we can just close our proof on line 4 because we got what we were trying to prove. And this is a rule of direct derivation. So you cite direct derivation. And then here's an example of simplification. So we want to show Q. We have P and Q as a premise. How can we get Q? Well, we know that if we have this AND claim, we can pull out either side of it, right? With our new rule, simplification. So we'll do that. We get Q from simplification on 2, right? Great, we got what we wanted to show. We wanted Q, we got Q. So we can close our direct derivation on line 3. There you go. Okay, let's continue with some more rules. At the end, I will show you how to combine these rules in proofs or something in a couple practice examples. All right. Okay, so those are the direct rules for the and symbol, but what about this or symbol here? Well, let's suppose it's true that Plato prances or Remy cooks ratatouille. Someone tells you that and you know it's true for some reason. From this one or claim, we know that at least one side of the or claim must be true, right? Because if this whole claim is true, Plato prances or Remy cooks ratatouille, then, at least one of these sides has got to be true. Either Plato prances or Remy cooks ratatouille. Sometimes both, but we'll talk about that later. That's not relevant right now. But at least one of these sides has to be true, right? So at least one of Plato prances or Remy cooks ratatouille has to be true. Well, suppose somehow you come to learn that Remy does not actually cook ratatouille. Suppose that's the case, which I know sounds insane, because Remy definitely cooks ratatouille. But suppose we find out he doesn't. Well, then we know for sure that Plato prances, right? Because at least one side of this big statement up top here has to be true. So if we know one side is false, the other side has to be true. So if you have, if Plato prances or Remy cooks ratatouille, then you find out Remy doesn't cook ratatouille. Well, now you're going to know that Plato prances. We'll do that kind of maneuvering in our derivations as well. So from something like P or Q and, that should be a D, and from not P, we can get Q, right? So if we have the premises P or Q and not P, then we can get Q, right? Because at least one side of this has to be true. Clearly P is not true, so we get Q. And also you can do it the other way. If you have P or Q and not Q, then you can get P, right? If the right side isn't true, you can get the left side. This rule will have a kind of Latin name, modus tollendo ponens, which we are going to abbreviate with MTP. I'll show you how to do that in a second. But this is how it looks. So you can see if we have not P and we have P or Q and we want to show Q, well, we have P or Q as a premise, we have not P as a premise, and then we can apply our new rule, modus tollendo ponens, to get Q, right? Because we know not P is true, which means P is false, which means Q has to be true, because at least one side of this or statement has to be true. Yeah, and you can do it the other way as well. If you have P or Q, you have not Q, well, with modus tollendo ponens on lines 2 and 3, you can get P, right? Okay. So that's our first rule for the or symbol. It's modus tollendo ponens. That's where we get rid of an or symbol by negating one of its sides and then getting the other side for free. But we can do this the other way as well. Suppose we know for sure that Plato prances, right? Well, from this one claim, we know that Plato prances or anything is a true claim, because there only needs to be one side of the or statement that is true for a whole or claim to be true, right? So if I know Plato prances, it's true that Plato prances or Remy cooks ratatouille. It's true that Plato prances or Remy doesn't cook ratatouille. It's true that Plato prances or the Lakers will win the NBA Finals. Or it's true that Plato prances or Canada is part of North America. It doesn't matter because we know at least one of these sides is true. In this case, Plato prances, right? Is true. So it can be or anything. Yeah. So in this case, if we know something, like P, for example, we can say that P or Q is true for any Q. Doesn't matter what the Q is. Seems a little weird, but that's the rule. That's how it's done in propositional logic. So from P as a premise, we can get P or Q. And also from Q, we can get P or Q. So that is, you can put the thing you know on either side of the or symbol. It doesn't matter. Okay, we're going to call this derivation rule addition because you know something and then you kind of add something to it with an or claim. And we're going to abbreviate it with ADD for addition. So in our proofs, the ADD rule, addition, it looks like this. Suppose you want to show P or Q. You already have P as a premise. So you can get P or Q by addition on the line that you're adding to. In this case, it's line 2. And similarly, if you want to do the other order, you'll have P or Q. And suppose you have Q as a premise. Well, then you can get P or Q by addition on line 2. Okay, so let's consider how this looks in doing it step by step in Carnap. And on the right side of the screen there, of course, you'll see the MTP and ADD rules are there, so you can keep an eye on them. But yeah, let's take a look at them. So in this case, we want to show P. We have P or Q, and we have not Q. We need to make sure our indents are good. These are both premises. Okay. Well, we know that P or Q is true, and we know that not Q is true. Since one side of this or statement has to be true, we know that P is true. So we'll get P. And what rule did we use for that? Well, we used modus tollendo ponens, right? And we did it using lines 2 and 3 because this negates one side of the or claim, so we're left with the other side. And there you go. That's our direct derivation. We showed what we were trying to show, and there it is. Okay, and what about our other rule that includes the or symbol? Well, suppose we want to show P or Q, and we have P, as a premise. Well, with our new rule addition, we can add anything using an or symbol to something we already know, right? So we can just write P or Q. Addition to what we have on line 2. And this will give us exactly what we were looking for, P or Q, right? So a direct derivation on line 3. And there you go. That's how you use it. Okay. And I will now go back to explaining our last couple of derivation rules before we move into some more complete examples. All right. So finally, we are going to learn some direct rules for the if and only if then symbol. Yeah, so it means if and only if. But what does this really mean in English, right? It's kind of a weird thing. We don't really say it very much. But if I'm saying, for example, that Plato prances if and only if Remy cooks ratatouille, then I'm saying Plato prances if Remy cooks ratatouille. That's what the if there is. And Plato only prances if Remy cooks ratatouille, right? That's what this part is. So what this is saying is that, if Plato prances, then Remy cooks ratatouille, right? Because the only times Plato prances are if Remy cooks ratatouille. But it's also saying that, anytime Remy cooks ratatouille, Plato prances. So it's saying, if Remy cooks ratatouille, then Plato prances. Yeah, so it's the two sides of it. If and only if symbol imply each other. It's kind of like putting two of our normal if then arrows, right? So it's saying anytime Plato prances, Remy cooks ratatouille, and anytime Remy cooks ratatouille, Plato prances. That's what the if and only if symbol is saying. So we know that if P and Q is true, or P if and only if Q is true, then we know that anytime P is true, Q will be too. And we also know that anytime Q is true, P will be as well. So P if and only if Q means that P arrow Q. And it also means that Q arrow is P. It just is a way of showing that they both imply each other. They're both if then about each other. which means that anytime that we have P if and only if Q, we can get if P then Q. And anytime we have P if and only if Q, then we can get if Q then P. So you can make it work either way, right? You can get both directions out of it. So we're going to call this the biconditional conditional rule, because we go from this big biconditional, this double arrow, to a simple conditional, this one little arrow, one direction arrow. So it's called the biconditional conditional rule, which means it's BC. This one's going to be BC. That's the name of our rule. So in our system, it'll look something like this. So you have P if and only if Q. You want to show if P then Q. Well, from the premise, P if and only if Q, you know you can get if P then Q by using BC on the line where you have the if and only if, which in this case is line 2. And you can also do it the other direction. So if you have, you want to show if Q then P, and as a premise you have P if and only if Q, then we know from our rule that you can get if Q then P by using biconditional conditional on line 2, right? You can break it down either direction. But the single arrow always has to point right. Keep that in mind. They can't point left. But you can, if you have this biconditional, you can spit out the arrow with either side of the biconditional on the left and either side of the biconditional on the right. Okay. And we can also consider this the other way, right? So if we know that if Plato prances, then Remy cooks ratatouille, and if we know also that if Remy cooks ratatouille, then Plato prances, then we know that both statements imply each other, right? And that, as we saw, is exactly what the double arrow, the if and only if, is saying. As anytime Plato prances, Remy will cook ratatouille, and anytime Remy cooks ratatouille, then Plato will prance, right? So this means that ultimately Plato prances if and only if Remy cooks ratatouille, or the other way around if you want. Yeah. So we can also go from two conditionals to a biconditional. So for example, if we have if P then Q and we have if Q then P, then we can get P if and only if Q, or Q if and only if P, right? Like if the P implies Q and Q implies P, then we know that they imply each other. So, we can define our rule as if we have P then Q and Q then P, then we can get P if and only if Q, or Q if and only if P. But this time we're going the other direction, right? The last rule I showed you was one where we went from the biconditional to the conditional. Well, in this case, we're going from two conditionals to a biconditional. So it's the other order, right? So this one we're going to call CB instead of BC. It's just the other direction, right? And this is how it will look in our proof. If we have if P then Q, and we have if Q then P, well, then we can get P if and only if Q. And we can also do it the other direction. If we have if P then Q, and we have if Q then P, then we can get Q if and only if P. That's fine. Okay, so let me show you how that looks in our system, step by step. All right. So in this case, we want to show P double arrow Q. We have P arrow Q as a premise. We have Q arrow P as a premise. And now what are we going to do to get this double arrow? Well, we can use our new rule, conditional biconditional, because in this case we're going from conditionals to produce a biconditional. So CB, we're going to use that to get what we are looking for. So we get P double arrow Q, and we can do conditional biconditional using lines 2 and 3, because those are the two conditionals we're using to build our new biconditional. And that's great. We used a rule of direct demonstration to get this, and it's directly shown in the proof. So we can do direct derivation on line 4. There you go. Similarly, to go the other way, using biconditional conditional, we can do P. Oh, I'm sorry. We want to show Q, arrow P. And as a premise, we have P, double arrow Q. Well, conveniently, we have this new rule, right? That lets us go from a biconditional to a conditional. That one is BC. So we will write Q, arrow P on biconditional to conditional on line 2. We only need to cite this line because you only need one double arrow to get whatever the arrow to go in which direction you want, whichever direction you want. So that's a rule of direct derivation that we use. It's in the proof, direct derivation on line 3. And you can see it's quite satisfied with us. So that's great. Okay. So let's consider that those are our new derivation rules. That's all of them. They're all pretty simple to understand, I think, conceptually. You just need to hammer them into your head by using them over and over. But this is the last content to learn for any propositional logic derivations. So now you've completed propositional logic derivations. Later in the course, hopefully we'll get to predicate logic derivations. But for now, that's it for propositional logic derivations. So yeah, keep on top of your problem sets as always. I'm going to show you some more practice. But always remind you to keep on top of your problem sets and do the practice exercises, ask questions in the live sessions. Be aware that the midterm is coming very soon. So, stay on top of things. And yeah, ask questions as needed, whatever. But for now, let's do some examples together to make it more, give you more experience seeing how the rules would be applied. Okay, so as always, we'll work through some examples, and as always, the examples are just found through Brightspace. Make sure, of course, you do the relevant problem set for this video, which is in Chapter 8. In fact, let's just take a quick look at it. The problem set you should be doing after you learn these rules is problem set 9. So do that when you can. Problem set 9 in Chapter 8. I'll just show you a few examples so you can see how this goes like normal. So what I'm doing is from the practice document, not from the problem set. Okay. So you can see I'm doing 1.7 here from the practice document. Let's figure out how to do this. So we have what we want to show is P. Then, as always, I like to list the premises first. You can copy and paste if you want, but I don't know. I'm just typing. Okay, so we want to get P. Well, how can we get P? Well, we know if we have R, then we can get P or not Q. And we know that if we can get Q, then we can get not Q, right? By double negation introduction, which means we could get the negation of the right side of this OR claim, and then give us P by modus tollendo ponens. So seeing all of that at once, that takes some practice, but you just try and see what you can work out as you go. So let's see. What can we do here? How can we get R? Well, we have this convenient AND symbol here that lets us get Q or R. So actually, let's just break them both down right now. Why don't we? So we can get Q from adjunction on line 2. So remember, adjunction is, we can get Q from simplification on line 2. You'll remember simplification is what lets us get rid of this AND symbol and break it into its parts. So we have Q and we have R now, right? Well, with R, we can get P or not Q, right? Because if we have R, then we can do modus ponens to get this. Modus ponens are our old and reliable friend. One of our very first rules. All right. So now we have P or not Q. Well, we have Q, so we can get not Q by double negation introduction on line 4. And with that, well, we have the negation of the right side of this or claim, right? And one side of this has to be true. It can't be not Q because we have not Q, so we get P. And that we get from modus tollendo ponens on line 6 and 7. And great, look at that, we have P now. Is what we were trying to show. We got it with a rule of direct derivation. One of the ones we learned was the last step, MTP. So direct derivation on line 8. Line 8 is where we got what we were trying to show. There you go. You can see it's all correct. What would be a good one to do next? Let's just do the next one. So we are trying to show not P or S. Our premises are Q and not R. And if P, then R. Okay. So we know that if we can get either side of this or claim, we can get the other one, right? Because you'll remember using addition, ADD rule, if we know something is true, we can say whatever we know is true or whatever we want. So if we want to get not P or S, we probably want to get not P because, you know, there's no S's in here that we could dig out. So let's first break down this AND claim. Let's simplify it using simplification. That way we'll have access to either side if we ever need it. So that's good. Well, you'll see that gives us a not R, right? Which means we can do modus tollens on this. Not R gives us not P by modus tollens, one of our early rules as well. So we get not P by modus tollens, not modus tollendo ponens, that's different, by modus tollens using lines 5 and 3. And then finally, now that we have a not P, well, we can say not P or anything, right? So we can do not P or S. And that is from addition on line 6, because we have the not P on line 6. And addition just lets us add an or whatever. And so again, we used a rule of direct derivation to get not P or S, which is what we were trying to show. So direct derivation, line 7. Look at that. Nice, huh? Only an 8-line proof. Let's see. What will have some interesting rules. Okay, let's do this one because I see it has a biconditional there. So we want to show P double arrow Q, or P if and only if Q. And then let's list our premises. We have R or Q as well. We have not P, arrow, not Q. All right, so those are our premises. So here, this is an interesting one because we need both that P implies Q and Q implies P, right? That's how we can get a double arrow in our proof. We have to get two conditionals that go either direction to make a biconditional. So that means we're probably going to need two nested conditional derivations. Just kind of ugly, but you know, let's do it. So first we want to show that P arrow Q, because we're also going to show Q arrow P, right? So let's, as always, when we're trying to show a conditional, we assume the left side, and now we got to get Q somehow. Well, with P we can get not R, from modus ponens on this, right? So we will get not R from modus ponens using lines 6 and 2. And look at this, with not R, we have this or statement, right? So we know if one side is not true, then the other side has to be. Well, we have not R, so we know R isn't true, so we can get Q. So we get Q, and that is by modus tollendo ponens. That's the one where we get rid of this or claim, using lines 7 and 3. Great, so now we've done a conditional derivation. We assumed P, and we got Q, right? So we got that on line 5. Or, sorry, we got that on line 8, which means we now have access to what is here on line 5. We now have access to P arrow Q. Okay, but we need to show also the other way. We need to show Q arrow P, right? So that we can get our biconditional, which is really what we want in the end. So in this scenario, again, we assume Q for a conditional derivation, a conditional proof, and we want to get P. Well, with Q, what can we do? Well, we see here we have not Q, so we have if not P, then not Q. So if we have the negation of this not Q, we can get the negation of this P, right? Well, that sounds like a good plan. So let's get not Q by double negation introduction on 11, right? Because you can always just introduce two negations to something that you have access to. All right, so with that, we can get not P, right, by modus tollens on line 4 here. On line 4, whoops, 4 and 12. And then from that, of course, we can get P, right? Because we can just get rid of the two negations here. So double negation elimination on line 13 gives us P. And look at that, we got exactly what we were trying. We assumed Q and we got P, so we got Q arrow P. So we'll close that conditional derivation. Remember, we're deriving a conditional on line 14. And great, so now we have access to what's on line 10, and we have access to what's on line 5, because we proved both of them. So now we can use our conditional biconditional rule, our CB rule, to combine these, right? Because we have if P then Q, and we have if Q then P. So we know that P, if and only if Q. And how did we do that? We went from our conditionals to our biconditionals. We went from C to B, so CB. And we did it using line 10, which we already have access to, and line 5, which we now have access to. And then, because this last step to get the P is a rule of direct derivation, and we directly showed what we were trying to get at, we have a direct derivation on line 16. And look at that. It's closed. It's happy. All is well. Woohoo. Okay. Let's do one more for now. And hopefully that will get you guys going in the right direction, yeah? Let's do 1.15. Because I see it has negations and biconditionals and all this stuff. Okay. So as always, we write that we want to show the conclusion. We list our premises. Okay, great. So how are we going to get Q? Well, we know that we can get... Let's break down what we can, and we'll see if we can figure it out. Because I need a moment to get this one too, myself. It isn't just coming to me straight away. But let's break down what we can, and that will give us more stuff to look at. So we know from this that we can get both if P then Q, or then not Q, and if not Q then P. So let's stick those out, right? Using our new biconditional conditional rules, right? Because we go from this biconditional to get our conditional on line 2. And let's do it the other way, just so we have access to it if we want. Right, because this can be broken down either direction. Great, okay. So what would be good is if we could get a not P, right? Because then we can get a negation of not Q, which is not Q, which will let us do a double negation elimination. So that's a good idea. Let's see how we could do that. Well, one way to get a not P is to assume P and show that you get a contradiction. So let's do that. Let's show, we want to show not P. So we're going to assume P and see if we can get a contradiction. So from P, we can get not Q, right? Actually, we don't even need this not Q, this modus ponens. Remember, from P, we can do, from any line we have, we can do a addition to get an or claim, right? Well, look at this one up here. Right here we have not P or S. But we know that we can get P or S by addition on line 7, right? Because if we assume P, well, then we can get P or whatever, just by our addition rule. But you'll see that contradicts with not P or S, one of our premises. I'm going to restate it so that these are next to each other. You can see them. If you wanted to, you wouldn't have to. You could skip this, but I restate it so you can see it, because you can restate your premises if you want. Okay, but look, there's a contradiction here. P or S and not P or S are directly in contradiction. So we know that not P has to be true, because if you assume P, then you get this contradiction, right? So now we get indirect derivation, because we assumed P, showed it led to a contradiction, and then we got not P. So we got our contradicting lines were 8 and 9, which means we now have access to not P, which is great. So now that we have access to not P on line 6, we can use modus tollens on this line 5. So we can get not Q by modus tollens on line 6 and 5. And the system is happy with that. And then, great, now we have this not Q. We can double negation elimination to get ourselves Q. And look at that. We got what we were trying to prove. Took me a moment to get that one, but there you go. Yeah, I haven't looked at that in a while. Okay. Now the last steps we used was a direct derivation rule to get Q, and we showed it directly and all that. So we have a direct derivation of what we were trying to show, which is Q. We have a direct derivation on line 12. Okay, great. So I have definitely used simplification. I've used BC and CB. I've used adjunctification, I think. I've used modus tollendo ponens. Okay. So I was showing you examples where everything is used, I believe. So there you go. I think that's a good way to a good set of things to start you off on. As always, just rewatch the video as needed, watch it at whatever pace is needed. Yeah, do the practice exercises, do the problem sets, and bring your questions to me. But besides that, that's all. So thanks for watching, and I will see you next time.